Good morning, dear students. Last class we studied about inductive effect and what are the applications of inductive effect. So, according to that, I have written some questions. So, arrange the following in the increasing order of. So, there are two questions. In first, arrange the following in the increasing order of acidic strength. So, arrange the following in the increasing order of acidic strength, and here arrange the following in the increasing order of basic strength. So, arrange the following. So, first one, acidic strength, and second one, basic strength in increasing order. Arrange them. So look here, that is COOH due to presence of carboxylic acid group, COOH group, this is acidic nature, and we know that presence of plus I effect decreases the acidic strength, while presence of minus I effect or minus I group increases the acidic strength. Here the CH3, it has plus I effect because it is electron releasing nature, so it releases electron, and NO2, it has a minus I effect, so it increases the acidic strength, it decreases the acidic strength. So in this way, if you compare between these three, then due to presence of CH3 group, the acidic strength decreases. So the increasing order of acidic strength. So first from lowest to highest, you have to write. So first is, that is toluic acid, COOH, CH3, this is least acidic. Then from, that is benzoic acid, that is COOH, and the acidic strength then comes to for nitrobenzoic acid. That is para-nitrobenzoic acid, this one para-nitrobenzoic acid, this one benzoic acid, and this one toluic acid, para-toluic acid. Okay. Similarly, in case of this, so this is the increasing order of acidic strength. Similarly, in case of question number 2, presence of plus I group, electron releasing group, increases the basic character, but presence of minus I group decreases the basic character. In this way, the increasing, so from that this is basic, and the basic character increases due to presence of methyl group, and the basic character decreases due to presence of NO2 group. In this way, the increasing order of basic strength increasing order is, so nitro group has lowest, if there is presence of NO2 group, it has least, NO2 here, sorry, so here given NH2, and here given NO2, known as para-nitrotoluene, and so para-nitroaniline, this is para-nitroaniline, and then that of aniline, this is then that of aniline, and then the acidic strength of NH2, it is para-aminotoluene. Okay, so this is the increasing order of basic strength, and this is the increasing order of acidic strength. Okay. So today here we are going to study another electron displacement effect, that is resonance or mesomeric effect. Already you know what is resonance in chemical bonding chapter. Okay. Let us discuss again what is this resonance. So when a molecule is represented by different structures just by changing the position of electron pair, not the atoms, then all the structures are known as resonance structures or contributing structures, and the phenomenon is known as resonance. So the presentation of a molecule just by changing the electron pairs, and which can explain the similar properties of the compounds, not all, but partially it can explain all the properties of the compounds, then the structures are known as canonical structures or contributing structures. Okay, so you know benzene can be represented by this. So if the atoms are changed their position, then that give rise to isomerism. So atoms have the same position, but the electrons are changed, that give rise to resonance structure. Look here, so benzene can be represented by this structure, or this can be represented by another structure. So this can be represented by this structure. So actually how this happens? So this bond will shift towards this, and this bond will shift to here, and this bond will shift to here. So in this way, the bond, this one comes here, and this one comes here, and this one comes here, we get this type of structure. And again, this bond can come here, this bond can come here, and this bond can come here. So in this way, it can give this structure. So these two structures are known as resonating structures or canonical structures or contributing structures. But these structures do not explain all the properties of the molecule or the compound. So actual structure is in between them. That is called the actual structure, which cannot be actually represented in pen and paper. That is actually known as the resonance hybrid. And the resonance hybrid explains all the properties. So we can represent, this can be represented by like this here. So the electrons are not at a fixed position. The pi electrons here are not at a fixed position. They are just changing their position. So in this way, after changing their position, in this way, these electrons are, you can say, these are delocalized. These electrons are delocalized. These are moving around this benzene nucleus. So in this way, we can represent this as like this. Okay. So this may be the resonance hybrid of benzene. Okay. So all the characteristic properties cannot be explained by this resonance. Look here. If this is, if this should be the structure of benzene, then if this should be the structure of the benzene, then here carbon 1, 2, 3, 4, 5, 6 carbon. So the carbon-carbon bond length should be different. If this is carbon-carbon double bond, here the bond length in this case, that should be 134 picometer, and if it is single bond, the bond length should be, it is 154 picometer. But actually experimentally it is found that all the carbon-carbon bond lengths are same. So in this way, the bond length is, that is 139 picometer. In this way, what type of bond present? So you can say this pi electrons. So the bond between carbon-carbon is in between double bond and a single bond. So in between double bond and single bond, in this way you can represent like this. So the bond length is found to be 139 picometer. So if this is double bond, then it should undergo addition reaction. But actually this benzene is more stable. These pi electrons are more stable. Pi bonds are more stable. In this way they undergo a substitution reaction instead of addition reaction. So all these properties cannot be explained by this structure, but somehow it tries to explain the characteristics properties. Okay. So what is the energy? This is the resonance hybrid, and the resonance hybrid has the least energy. Okay, and these structures have also some energy. If we express this structure, these structures have also some energy. And what is the difference between these structures? What is the difference between energy of this structure and the actual resonance hybrid? That is known as the resonance energy. So that energy is known as resonance energy. So the energy difference between the most stable resonance hybrid structure and the contributing structure is known as resonance energy. Okay. Next, what are the conditions to write the resonance? What are the conditions and the characteristics of resonance? So for the resonance, the atoms do not change their position, only the electron pairs change their position. This is the first condition. And resonance actually possible in case there is planar structure. So look here, if for resonance we should require a pi bond, pi electron. This is cyclohexene, no resonance possible here. This is cyclohexadiene. In this case also no resonance possible. So for the what is the condition then? For the resonance there should be a conjugation. Conjugation means there should be alternate position, the pi bond that should present at alternate position. Some pi bond, some lone pair of electrons, some positive charge, some negative charge, if present at alternate position to this pi bond, then only the resonance is possible. Look here, so resonance is possible when the resonance is possible in case these are in conjugation. Look here, suppose CH2 double bond C, then single bond CH, and there is suppose instead of C, it is suppose written CH2 double bond C and H and CH and double bond CH2. So in this case, this is in conjugation. So pi bond is at alternate position. Pi bond, single bond, double bond, single bond, double bond. Or pi bond, one sigma bond, only sigma bond and pi bond. So pi bonds are present at alternate position. And another case of it is possible, CH2 double bond CH. If there is any lone pair of electron, then also resonance is possible. And resonance is also possible when there is a positive charge, let's suppose carbon, positive charge is present, or resonance is also possible if there is a alternate position, if there is a negative charge is present. So in this case, negative charge is present, then the electron pair comes here and this comes here. So in this case, the relative structure of this is CH2, here minus, single bond, CH, double bond C. Okay, in this way, whatever groups are present may be there. If there is a negative charge, then electron flow towards it. In this way, this is the resonance structure of this negative charge. And if positive charge is present, then this electron pair comes here. Okay. So in this way, the electron pair comes here. So the relative structures of this regime, CH2, here positive charge, single bond CH, double bond C, and if there is positive charge, if the electron pairs come here, then no charge. There should be no charge. And from where electron comes, if this is neutral, then it carries a positive charge. If this carries negative charge, then it carries no charge. So first from where electron, and to where the electron goes, if it carries positive charge, then no charge, and if it carries no charge, then it gets a positive, then if it carries no charge, then it gets a negative charge. So in this way, you have to assign the charges. Look here, if this type of, if a double bond is in conjugation with an atom having lone pair electron or unshaped pair electron, then the unshaped pair electron moves towards this. So in this way, it groups comes here and it comes here. Okay, and the resonance structure of this should be CH2. So from where it comes, it should carry positive charge, as it is neutral. It should carry positive charge, and to where the electron pair goes, it carries negative charge. So this is the resonance structure of this. And as this is symmetrical, look here, what is present here and here, any direction you can write the resonance. In this way it comes here and it comes here. So the structure, resonative structure are CH2 minus, single bond, CH, double bond, CH, single bond, CH, here plus and here minus. So in this way we can write the resonative structure. Okay, we can write the resonative structure of different molecules. So when a pi bond in conjugation, when a lone pair in conjugation, when a positive charge in conjugation, when a negative charge in conjugation, then resonance is possible. That means at alternate position, the pi bond should be present at alternate position to a pi bond, to a lone pair of electron, to a positive charge, to a negative charge, then it is resonance possible. Next, resonance structure which carries more number of covalent structure, that has more contribution towards the resonance hybrid, that means that is more stable. Okay, and the resonating structure If there is resonance structure with charge separation and without charge separation, then the resonating structure without charge separation is more stable than the resonance structure with charge separation. Okay. Next, if there are different atoms attached, if the negative charge carries negative charge bears electronegative atom and a positive charge bears electropositive atom, then that resonance structure has more contribution than other. That means if suppose some structure is given, a negative charge is given to look here, one thing here. Suppose CH2 double bond CH and C double bond OH is there. So we can write the resonance structure of this. So double bond, single bond and lone pair of electrons and double bond, single bond and double bond is present. As double bond, single bond and double bond are present, in this can have different resonance structures. So what are the possible resonance structures of this? Look here, this comes here and this comes here. In this way, we can write CH2 plus CH double bond C and here O minus and here H. This is another structure, and another one is also possible. If this comes here and this one comes here, then another resonance structure is possible, that is CH2 minus, then CH, then double bond and C, here O plus and H. Atoms have the same position, only electron pairs change their position. Look here, so different resonance structures can be written like this, 1, 2 and 3. So among these three, look here, the structure 1 is without any charge and here more number of covalent present, 1, 2, 3, 4, 5, 6. All other are there. So in carbon and oxygen if you count 1, 2, 3, 4, 5 present, and in this case 4 are present. So more number of covalent bond means more stable. So this structure is more stable. And another thing, this is without charge separation, and structure 2 and 3 these are with charge separation. So with charge separation means these are least stable and this is more stable structure. Next, if the negative charge on negative atom and positive charge on positive atom, that is more stable than other. So if we compare between these two, then this one is more stable than this. Because oxygen is electronegative charge, it carries a negative charge, and carbon is positive, then oxygen it carries positive charge. But here, between carbon and oxygen, carbon is positive but it carries negative charge. Here oxygen is negative but carries positive charge. In this case, it has least stable. So if we write the resonance structures, the stability order of different resonating structures, then the stability order of different resonating structures, then what is the stability order? The structure 1 is more stable, structure 1 is more stable, then structure 2, then structure 3. That means it has more contribution towards the resonance hybrid. Okay. So write down what is resonance and what are the conditions for resonance. So resonance and mesomeric effect. So if a molecule having certain molecular formula can be represented by different structural formula which differ in the arrangement of electron pairs and not the atoms, such like structures are called resonating structures or contributing or canonical structures. So these two are contributing structures or canonical structures, and these are numbered as 1 and this is numbered as 2. Okay. Structures, atoms or structures are called resonating structures or contributing structures or canonical structures, and this phenomenon is called resonance. So the compound as a whole cannot be represented by any of the structures. Actually, it explains the properties. The actual structure of benzene is different from these two structures. Okay. So resonance, the compound as a whole cannot be represented by any one of the structure, but as a hybrid called resonance hybrid. So in between these two, resonance hybrid with characteristics of all contributing structures. So the resonance hybrid has characteristics of all these contributing structures. So the different structures separated by double-headed arrow. So note down these. Okay, write down the points or conditions for writing the resonance structures. So all the resonance structures should have same atomic positions. So atoms do not their position. If the atom change their position, then it gives rise to isomer. So all the resonance structures should have same number of paired and unpaired electrons. If the paired and unpaired electrons may change in the form of some cases, the paired electron change in the form of some bonds. The resonance structures should have nearly same energy. The contributing structure should be so written that the negative charge should be present on electronegative atom and positive charge should be present on electropositive atom. The same charge, that is positive or negative, that should not present at adjacent positions. There may be some gap, so positive or negative charges should not present on adjacent position. If one positive charge, after that one negative charge, or in some cases some bond, then negative charge, like this. But if positive, negative, that should not present on adjacent positions. Next, the pi bond should be on conjugation with a double bond or a lone pair of electron or a positive charge or a negative charge. So note down these points. Next, come to what are the characteristics of resonance. So already discussed. So resonance structures with charge separation has less contribution towards the actual structure than resonance structure with charge separation. So look here, this is given one compound, that is propynyl. So this structure has without charge separation, and this is with charge separation. So two different charges are there, plus and minus charge. So it has less contribution towards the actual structure, or this structure is less stable than this one. So this one is more stable. Okay. Similarly, and again given, resonance structures with more number of covalent bonds have more contribution towards the actual structure. That means this structure is more stable form. So CH2, look here, how many covalent bonds? 1, 2, 3, 4, 5, 6, 7, 8, 9 covalent bonds are there, and here 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8 number of covalent bonds are there. So in this case, this has less contribution than this. More number of covalent bond, more contribution towards the actual structure, and without charge separation has more contribution towards the actual structure. That means that structure is more stable. Okay. So because of resonance, the bond length in resonance structures become equal. So in benzene, already I have explained, in benzene the carbon-carbon bond length, that should be the single bond, then the bond length should be 154 picometer, and this is the carbon-carbon double bond, then that should be 134 picometer. But actually that is in between 1.39. So how picometer? How this is possible? That is due to resonance. All the bond lengths of carbon-carbon in benzene become equal. That is due to resonance. Next, similarly in all other cases also the same. The resonance hybrid has less energy and greater stability than any of the structures. What is the resonance hybrid? That actually cannot be represented. So that is known as the resonance hybrid. The actual structure is known as the resonance hybrid. Thus, that has less energy than these contributing structures. Okay. So greater the resonance and resonance energy, greater is the stability of the molecule. And for resonance, it is condition. One condition is that there should be a coplanar. That should all remain in the same plane. That means there should be generally hybridization of sp2 hybridization if there possible. Then resonance is more easily. The resonance is feasible at that case. And if any structural modification that destroys the coplanarity, then it hinders the resonance. That should the molecule remain in a plane. That means it should have the carbon atoms should undergo sp2 hybridization. Then resonance, you can write resonance easily. Okay, so write down all these. So we already know how to write the resonative structures, in which case this resonance is possible. So for one condition is that there should be the pi bond should be in conjugation. The pi bond should be in conjugation with either with a double bond or with a positive charge, with a negative charge, or with a lone pair of electron. So already we have discussed what is CH2 double bond CH double single bond CH and double bond CH2. If this is there, then so the pi bond is in conjugation. That means an alternate position of a double bond or an alternate position of a positive charge or negative charge or a lone pair of electron CH2 double bond CH, and suppose any other atom is there having with a lone pair of electron, then so resonance is possible. So in this case, this resonance is possible. So if this type of is there, then resonance is possible. So if this resonance is there, then how to write the structure already we have discussed. Already we have discussed how to write the ready structures. Look here. So due to resonance, the flow of electron takes place. In all cases, due to this resonance, this flow of electron takes place. So the flow of electron takes place. So due to this flow of electron, there arises electron density in some atom, increase in electron density, and in some cases there is electron less in decrease in electron density. If this comes here and this comes here, we can write that is CH2 plus and CH double bond CH and CH2 minus. So in this case the electron density increases and in this case the electron density decreases. So flow of electron takes place. So this due to this flow of electron, as the flow of electron takes place, this resonance effect. This effect is called the resonance effect or mesomeric effect. So due to which this resonance effect and mesomeric effect, this is classified into two types. That is plus R effect. One is plus R effect, also known as plus M effect, and another minus R effect or minus M effect. Plus R effect or plus M effect, minus R effect, minus M effect, mesomeric effect. So in this way, due to resonance, so this resonance is classified into two types, plus R effect and minus R effect. So if a group or substituent is present, so that it gives an electron towards the system, the conjugated system, it gives the electron, then that effect is called plus R effect or plus M effect. So if any pi bond or lone pair is present, then it gives electron towards a system, that is a conjugated system, then that is called plus R effect and plus M effect. Look here, suppose there is benzene is there, and here suppose one chlorine atom is there. So this chlorine atom has shared pair of electrons. This is the conjugated system. Pi bonds are present at alternate position. If the pi bonds are present at alternate position, then first a pi bond, single bond, then lone pair electron or unsaid pair electron. Then it gives electron towards here, and this bond again forms. This bond comes to this carbon atom. In this way, this structure we can get. This structure is like this. So here no negative. Here we get a negative charge, and here some double bond character, and this charge chlorine. Okay, as when electron comes from any atom, we have to give that positive charge. This is neutral. This is negative charge. Then no charge. We have to give no charge. So positive, and here a negative. To where this electron comes, to that we have given negative. So in this way, this electron gives. So it shares this electron, the flow of electron takes place towards the system, that is called. So that groups are called plus R effect, plus R groups or plus M groups, and that effect is called plus R effect. Similarly, if any group present which withdraws electron pair from the system, that are known as your minus R and minus M effects. Look here. One example here, suppose to this another NO2 group is present. You know this is the NO2 structure. So there is a look here, double bond, single bond, double bond, single bond, double bond, single bond, double bond, all in alternate position. So as it is in alternate position, that is in conjugation, then oxygen is more electronegative than nitrogen. So this bond, this pi bond shifted towards this oxygen. So as the pi bond shifted towards the oxygen, now this oxygen gets negative charge, this nitrogen gets positive charge. To compensate the positive charge of nitrogen, this electron pair move towards nitrogen. So what happens as a result? If this electron pair moves, as a result, nitrogen here, this oxygen atom no change, and here one negative charge, and a double bond appears here. So as the bond comes to this nitrogen, so it forms this bond shifted towards this nitrogen carbon. So a double bond appears here, and here a positive charge, and all these two remain like this. So now, this group, this nitro group, withdraws electron. It takes electron from the conjugated system. Here it gives electron towards this conjugated system. So any group which gives electron towards this conjugated system, that added electron, that are known as a plus R effect or plus M effect, and which withdraws electron, that shows minus R effect and minus M effect. Okay, so nitro group, CHO group, aldehyde group, carboxylic acid group. So these groups are electron withdrawing nature. They exhibit plus R effect. Whereas chlorine group, halogen, presence of halogen, amino group, and hydroxy group, this group gives electron towards this benzene nucleus or towards this system. In this way, that are known as plus R and plus M effect. Okay. So note down. Next come to the types of resonance effect. Okay. So what is the resonance? So you know, due to resonance, there is flow of electron takes place. So due to flow of electrons, some positive charge or negative charge developed on some atoms. So due to this flow of electron, positive charge and negative charge develops. So this effect is known as resonance effect or mesomeric effect. So this is again classified into two types. One is plus R effect, another minus R effect. So plus R effect, if a group is attached to a conjugated system, so that it gives electron to the conjugated system, then that is known as it gives electron to the conjugated system, then that effect is known as plus R effect. Or from the group, away from the group, if this electron displacement takes place, then that groups are plus R groups, and that effect is called plus R effect. So any atom having a on-shared pair of electrons or having negative charge generally exhibit this plus R or plus M effect. OH group, OR, NH2, NHR, SH, X. So look here, in all cases there is on-shared pair of electrons. So when this on-shared pair of electrons is in conjugation and away from the atom, this displacement of electron takes place. So this electron pair comes here and this electron pair comes here. In this way there is a negative charge and a double bond is formed, and this atom carries positive charge. So a pair of electron goes, so negative charge, positive charge, and this type of effect is known as plus. To this system or towards the conjugated system it gives, towards the system it gives, or away from the group. If the electron displacement takes place, it is known as a plus R effect or plus M effect. Similarly, if any group is attached with the electron displacement takes place towards it or away from the conjugated system or from the conjugated system, then that is known as minus R or minus M effect. So such groups are NO2, CO, CHO, COH, CN. Look here, CHO present, oxygen is more electronegative, which withdraws electron from here in this way. To compensate this charge, again this pair of electron comes here. So double bond is developed there, and as electron displacement takes place from this carbon, here a positive charge developed, positive charge, and as the electron moves towards it, it carries a negative charge. In this way, these are the resonance structures of the other resonance structures, and this effect of CHO is known as minus R or minus M effect. Okay, so note down this. So now I think you are clear what is resonance, what are the conditions of resonance, what is the characteristics, and what are the types of resonance. Now next come to what are the applications of resonance, or what the application of this resonance effect. So the concept of resonance is applicable to explain the acidic strength, the basic strength, the relative acidic strength of different compound, the reactivity or the stability, the extra stability. So different physical and chemical properties of organic compounds can be explained on the basis of this resonance. So resonance plays important role in explaining these properties. So why some compounds are more reactive than other, why some compounds are less acidic than some other, why some compounds are more basic or less basic than other. So all these phenomenon can be explained by, all these concepts can be explained by the applications of resonance effect. Let us first discuss how it explains the acidic nature of carboxylic acids. So resonance effect explains the acidic nature of carboxylic acids. So we know the presence of electron withdrawing group increases the acidic character. Presence of electron donating group that decreases the acidic character. That is according to Yotti repeat. But why this carboxylic acid is acidic? That can be explained on the basis of resonance effect. So the relative structure of carboxylic acid is RC double bond OH. This is the relative structure. This is the structure of carboxylic acid. Functional groups RCOH. So here, two bonds of oxygen are there, and another two electron pair are there. And here two bonds are there, and here also two unstable pair of electrons are there. Look here. So double bond, single bond, and a lone pair of electron, and two lone pair of electron. And this is in conjugation. So double here the lone pair are directly attached with this atom, but here this lone pair is in conjugation, alternate position of this double bond. Double bond, single bond, and atom having lone pair of electrons. In this, if this type of, then this so this OH, this group is now exhibits the plus sign effect. So electron is away from this. In this electron pair moves towards it, and as the electron pair moves towards it, the electron pair total moves towards it, there is a formation of double bond here. So here a double bond is formed, and now the carbon valence becomes 1, 2, 3, 4, 5, and the valence becomes 5. Now this electron pair again comes towards oxygen atom. And now the oxygen atom has one electron here and one electron from carbon. And when the electron pair comes here, this is now the oxygen atom has two electrons. So one electron pair, or we can say the bond comes towards this oxygen atom. So as a bond comes means two electron comes. So one electron is of oxygen and another from carbon. In this it carries one negative charge. So the resulting structure of this carboxylic acid is RC. Now O minus. So one negative charge means here a pair of electron and here a double bond is formed. And now as the electron comes from here, so one electron pair comes and one remain on oxygen, one side by oxygen, and one goes to carbon. In this way, it has some positive charge and H. Okay, so RCOH, RCOH. This is the relative structure of carboxylic acid. So from here, what do we know? At the resolution of carboxylic acid, the oxygen atom gets positive charge. But you know, oxygen is electronegative nature, so it attracts the shared pair of electron. In this way, it attracts, it is electronegative and it carries positive charge. In this way, it attracts the electron pair towards it, and the removal of H plus takes place. In this way, so any substance which gives H plus is known as acid, and the removal of H plus takes place, it gives an acid. So this is the structure of, this is the resulting structure of carboxylic acid. Okay, another way we can also explain, look here, R, C, double bond O, and look here. So this carboxylic acid, after giving H plus ion, R, C, O, instead of this I am writing like this, R, C, O, H, after giving H plus ion, it forms RCOO minus. RC, when it gives H plus ion, double bond O and O minus. Plus H plus, so H plus means here 3 electron and here 2 electron. Okay. Now this RCO minus again undergo resonance. RCOO minus 1, 2, 3, 4. In this way, there is electron pair. So this electron pair comes here and this electron pair comes here. And the resonative structures of this carboxylate ion is RCO minus and double bond O, and here no electron pair. Look here. So these are the two resonative structures of one carboxylate ion. This is the resonative structures of carboxylic acid. So when we consider about carboxylate ion is more stable because this is without charge separation, but there is with charge separation. So resonative structures without charge separation is more stable than this. In this way, carboxylic acid by giving H plus ion forms carboxylate ion which is resonance stabilized. Hence, carboxylic acid is acidic in nature. Okay. So, you have known this is your carboxylic acid. Carboxylic acid. This is carboxylate ion. Carboxylate ion. So, the acidic nature of carboxylic acid is due to the release of H plus ion, in aqueous solution. So, carboxylic acid exists in two resonating forms, here two resonating form. In this way, due to resonance, the oxygen acquires the positive charge, for which, so O and H plus, for two positive do not remain at a time, so it cannot exist, and this release of H plus become easier. Or we can say as oxygen is more electronegative and positive charge developed, it attracts the pair of electron towards it by releasing H plus ion. So in this way, it facilitates the release of H plus ion. So as the positive charge developed on the OH atom, it releases the H plus ion. So again, this carboxylic acid, after releasing this H plus ion, forms this carboxylate ion, and this carboxylate ion is also resonance stabilized. So when we compare between the resonance structure of carboxylic acid and carboxylate ion, this carboxylate ion is more stable because this is without charge separation. Only one charge is playing here, but here two different charges are there. This is charge separation. In this way, carboxylic acid by one giving an H plus ion is stabilized to form carboxylate ion and release H plus ion. Hence, this one is acidic in nature. So note down this. Next, come to some other applications. Number 2, it explains the acidic character of phenol. It explains the acidic character of phenol. Look at what are the resonative structures of phenol. So phenol, this is the phenyl group to which if one OH group is attached, so this is known as phenol. So it undergo resonance. Look at how to write the resonative structures of phenol. So phenol OH. So first double bond, single bond, then lone pair, all are in conjugation. In this way, this electron pair comes towards this. So first electron pair comes, it forms a bond, and a bond moves towards another carbon, the adjacent carbon. Okay. So in this way, the next structure of this is here double bond, O, H, and one electron pair is also there and a positive charge, and here electron pair and it carries the negative charge, and all these two electrons remain as such. Next, so these are the different. next this electron pair comes to form a bond here, and this bond again comes to the nearest carbon atom to form a electron pair. So in this way, the next structure is here double bond OH, here is the positive charge, bond here, electron pair, but it carries negative charge. So again this electron pair moves to the nearest carbon, nearest bond, and the double bond comes to the nearest carbon. And here again this bond comes to this carbon atom. In this way, the next reductive structure of phenol is double bond OH. Here also a pair of electron. Although there is a pair of electron, there is positive charge. Bond like this, a new bond form, and here the electron pair and negative charge. Okay. So again, this electron pair comes to the adjacent bond, and this electron pair comes to this oxygen again. So in this way, the structure is here OH. Okay, so again same. The structure 1 and structure 2 are similar. 1, 2, 3 and 4 and 5. There are 5 regenerative structures. Okay. So in this way, by this regenerative structure, we find that the oxygen atom, this is electronegative and it carries positive charge. So resonance condition is the electronegative atom should carry the negative charge and the positive atom should carry positive charge, but still it is a negative or negative atom carries positive charge. And hence the electron pair comes towards oxygen and release of H plus become easier. Similarly, this phenol, so in this way, this oxygen atom gets positive charge. So as it gets positive charge and it is being electronegative nature, it attracts the electron pair towards it. As a result, release of H plus become easier. And again, this phenol, after giving this H plus ion, forms phenoxide ion. It forms this phenoxide ion, and this phenoxide ion is also resonance stabilized. So it forms this phenoxide ion, and this phenoxide, this is O after minus H plus, gives phenoxide ion or phenate ion. This is phenoxide ion and this is phenol. And this phenoxide ion is also resonance stabilized. Look here. So you have to also write these regenerative structures. 1, 2, 3, 4 bonds are there. Okay. So if one electron pair comes here, in this way 6. So again one electron pair comes here and this bond comes here. So in this way, next structure is, this is O. Now no negative charge here, and this carries the negative charge. And again, and all these two remain as such. And again what happens? And again this electron pair, so this is a pair of electron, this again comes to form a bond, and this bond forms a pair of electron. In this way, next structure is, this is O, one charge, one bond, and here negative charge with pair of electron. And again this come to form. So electron pair forms a bond and the bond forms electron pair. Remember this. So in this way, next regenerative structure is double bond O, electron pair, bond like this, and again this bond here, and as it comes to a bond, see here electron pair comes here with this negative charge. And after that what happens? And again flow of electron takes place. This flow of electron pair again comes to form a bond, and this bond again comes to the nearest atom, that is oxygen. So So next structure again found to be, that is O minus and okay. So these are also 5 resonating or contributing structures. Number them as 1 to 5. Okay. So among the 5 structures, look here, both phenol and phenoxide ion, both are resonance stabilized, both have resonant structures, but phenoxide ion is more stable than this because this is with charge separation, plus and minus charge is there, and positive atom is on oxygen atom. And here positive charge, so negative charge on electronegative atom, and there is no charge separation. In this phenoxide ion is more stable. Hence phenol giving by H plus ion forms phenoxide ion, hence acts as an acid. So first write down these relative structures, then I will give you the explanation. So write down this. So next come to the explanation. So phenol exists in 5 resonative structures. First we have to draw these resonance diagrams. 5 resonance structures. Due to resonance, the oxygen atom of OH group acquires a positive charge and oxygen being electronegative attaches the shared pair of electron of OH group towards it and releases H plus ion. Further, phenol after giving H plus ion forms phenoxide ion, which is also resonance stabilized. This phenoxide ion also forms 5 resonative structure, but that one is more stable than phenol because that has without charge separation and phenol has with charge separation. And another in phenol, the oxygen atom, electronegative atom gets positive charge, and in phenoxide, the oxygen atom gets the negative charge. In this, phenoxide ion is more stable than phenol. So, in this way, phenol gives H plus ion and forms phenoxide ion, which is resonance stabilized. So, as more stable form is phenoxide, so phenol gives H plus ion, hence phenol is acidic in nature. Next, come to another application, that is aniline is less basic than methylamine. So, methylamine has structure CH3 and H2. Here it gives electron towards nitrogen, electron density increases. In this way it becomes more basic. But aniline, it exists in resonance form. Okay, aniline exists in different resonating forms. Look here, what is the resonance structure of aniline? So this one is, you can write also like this. Here by giving electron pair. So double bond, single bond, and an atom. Double bond, single bond, and an atom having lone pair of electron. Here single bond, double bond, single bond, and an atom having lone pair of electron. In this way, first this bond comes towards this, and a bond, electron pair forms a bond, and the bond forms pair of electron. So here we get another structure, that is double bond here, NH2 plus, and these two bonds remain same, and here a pair of electron with this negative charge. And after that, this electron pair move towards here, forms a bond adjacent position. When electron pair, single bond, double bond, always look at the conjugation. In this way, flow of electron takes place, and this bond again comes towards it. So in this way, next structure is like this. This is NH2 plus, here double bond, and here a new bond is formed, and this electron pair with this negative charge comes here, and again this comes here, and this bond, again this electron pair forms a bond, and the bond which is the adjacent position with the bond that forms adjacent position with the bond that forms the electron pair in the next carbon atom. So in this way it forms double bond and H2. So here an electron pair with negative charge and new bond is formed in this way. And here the positive charge as well. And again this electron pair, now electron pair single bond, double bond, in this way it forms bond, and this bond again comes to the nearest atom, near atom. So in this way, next resulting structure is single bond NH2 with its pair of electrons. So due to resonance, the structure 1, 2, 3, 4 and 5. So due to resonance, the nitrogen atom get positive charge, the electron density of nitrogen atom decreases, for which receive of H plus become difficult or the donation of electron pair become difficult. In this way, it becomes less basic than that of methylamine. While in methylamine, due to increase in electron density, this is more basic, but here this aniline is less basic. Okay, so first explanation. So in aniline is less basic than methylamine. So in methylamine, due to inductive effect, the electron density on nitrogen atom increases. So for which donation of pair of electron becomes easier, or protonation becomes easier. But in case of aniline, due to resonance, the nitrogen atom get positive charge. So the electron density of nitrogen atom decreases. As the electron density decreases, the electron density decreases. As the electron density decreases, so donation of pair of electron becomes difficult, as well as receive of H plus also become difficult. Protonation becomes difficult. So as positive charge it cannot receive H plus ion, so receive of H plus become difficult. Hence aniline is less basic than methylamine. So note down this. So already you have drawn the structure. Now note down the sentences.